Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, we are from group 3 and now we're gonna presentation about the completeness property of R. But before that, let us introduce our member. The first one is I. My name is Widaswara Agustin Hanisha with ID number 057, and the second is Febriana with ID number 102. The third is Bagus Surya Maulana with ID number 126. And the last is Hilila Widatina Victorinada with ID number 132. One more property of R that is often called the completeness property. This additional property, the completeness or the supremum property, is an essential property of R, and we will say that R is a complete ordered field. It is the special property that permits us to define and develop the various limiting procedures. Now, we enter the first definition. 2.3.1 definition state that let big S be a non-empty subset of R. A. The set big S is said to be bounded above if there exists a number small u element of R such that small s less than or equals to small u for all small s element of big S. Each such number small u is called an upper bound of big S. B. The set big S is said to be bounded below if there exists a number small w element of R such that small w less than or equals to small s for all small s element of big S. Each such number small w is called a lower bound of big S. C. A set is said to be bounded if it is both bounded above and bounded below. A set is said to be unbounded if it is not bounded. For example, the set S defined by x element R such that x less than 2 is bounded above. The number 2 and any number larger than 2 is an upper bound of S. This set has no lower bounds, so that the set is not bounded below. Thus, it is unbounded, even though it is bounded above. Okay, for the next presentation, will be presented by my friend, please.
And then if there is supremum or the infimum of a set S exists, we will denote them by sub S and inf F. So the next is a possibility that have in here. There is a four possibility for a non-empty set subset S of R. That is the first one is have a supremum infimum, have a supremum but no infimum, have an infimum but no supremum, have neither a supremum nor an infimum. The definition of O the definition of O equals sub S asserts that U is an upper bound of S such that U is less than or equal to V for any upper bound of F of upper bound of V of F. It is useful to have learned with to expressing the idea that U is the least of the upper bound of S. One way to be observed that any number smaller than U is not upper bound of F, that is, if G less than O, then Z is not upper bound of S. But to say that G is not upper bound of S means there exists an element SG in S such that G is less than SG. Similarly, if epsilon is greater than 0, then U minus epsilon is smaller than U and thus forced to be an upper bound of S. The following statement about an upper bound U of a set S are equivalent. The first one is if V is any upper bound of S, then U is less than or equal to V. If Z is less than U, then Z is an upper bound of S. If z is less than u, then there is exists fc element of S such that g is less than fc. If epsilon greater than 0, then there is exists as epsilon element of S such that u minus epsilon is less than or equal to S epsilon. Therefore, we can state two alternate formulations for the supremum. So the next slide will be explained by my friend.
Okay, the next is lemma. A number u is the supranom of a non-empty subset S of R if and only if u satisfy the conditions. The first condition is small s less than or equal to u for all s in big S, and the second condition is if v less than u, then there exists small s accent in big S such that v less than s accent. For future work with limits, it's useful to have these conditions expressed in terms of e greater than 0. This is done in the next lemma.
Next, an upper bound U of a non-empty set big S in R is the supremum of big S if and only if for every epsilon greater than 0 there exists an little s epsilon element big S such that U minus epsilon is less than little s epsilon. For the proof, if U is an upper bound of big S that satisfies the stated condition, and if V less than U, then we put epsilon equals to U minus V, then epsilon greater than 0. So there exists little s x epsilon element big S such that V equals U minus epsilon less than little s epsilon. Therefore, V is not an upper bound of S, and we conclude that U equals to supremum big S. Conversely, suppose that U equals to sub big S and let epsilon greater than 0, since U minus epsilon is less than U. Then U minus A is not an upper bound of big S. Therefore, some element C of big S must be greater than U element A. That is, U minus A less than little s epsilon.
This example, there are three examples here, and the first example is if a non-empty set S1 has a finite number of elements, then it can be shown that S1 has a largest element U and a least element W. Then U equals to supremum S1 and W equal to infimum S1, and they are both elements of S1. This is clear that if S1 has only one element, and it can be proved by induction on the number of elements in S1. It's like on the exercise 12 and 13. The next example is the set S2 all of x such that x greater than or equals to 0 and less than or equal to 1 clearly has 1 for an upper bound. We prove that 1 is a supremum as follows. If v less than 1, there exists an element s accent in S2 such that v less than s accent, and name one such element as accent. Therefore, v is not an upper bound of S2, and since v is an arbitrary number, v less than 1, we conclude that supremum S2 equals to 1. Its similarity shown that infimum S2 equal to 0. Note that both the supremum and the infimum of S2 are contained in S2. The next example, the third example, is the set S3 all of x such that x greater than 0 and less than 1 clearly has 1 for an upper bound. Using the same argument as given in B, we see that supremum S3 equal to 1, and in this case, the set S3 does not contain its supremum. Similarly, infimum S3 equals to 0 is not contained in S3. Okay, the next is the completeness property of R. Every non-empty set of real number that has an upper bound also has a supremum in R. This property is also called the supremum property of R. The analogous property of infima can be deduced from the completeness property as follows. Suppose that S is a non-empty subset of R that is bounded below. Then the non-empty set of S uh, all of minus S such that S in S is bounded above, then the supranom property implies that U is supranom S exists in R. The reader should verify in detail that minus U is the infinitum of S. I think that's all from us. I'm sorry if there is some mistake, and thanks for your attention. Wassalamualaikum warahmatullahi wabarakatuh.